Hello, my name is Samantha Scales, and this is my video lab report for Lab 3, Black Hole and Orbits. So for the purpose of this lab, in Part 1, we're given position data of a star orbiting a black hole. We use that to calculate velocity, momentum, and the net force, and from there extract the black hole's mass. In Part 2, we calculate all gravitational forces each time step to predict where the moon and ship move next, and find a ship velocity that creates a stable orbit around both bodies without crashing. The core equation for both parts is Newton's second law in momentum form. F net equals dp over dt, approximated as delta p over dt. We use this approximation because we only have discrete data points, not a continuous function, so dividing the change in momentum by the time step is the best estimate we can get. For gravity, the force equals g times both masses divided by distance squared, and it's always attractive. This is the only force acting in both parts of the lab. We also break F net into two components: the parallel component in the direction of motion. This only changes the star's speed, not its direction. The perpendicular component is at a right angle to motion. This is what actually curves the orbit without speeding the star up or slowing it down. We separate them because F net as a whole tells you how momentum is changing as a vector, but F parallel only tells you how the magnitude is changing. They're not the same thing. Now for the results of this lab, in part 1, I got a slightly different mass of the black hole each iteration due to numerical approximation, so I averaged all values and got 1.92 times 10 to the 34th kilograms. That's around 10,000 times bigger than our sun's mass. In part 2, circular orbital speed at the ship's distance is about 676 meters per second. I chose Vx equals negative 400 and Vy equals negative 550, giving total speeds of about 680 meters per second. The ship has successfully orbited both bodies without crashing. For system and surroundings, in part 1, the system is a star, and the black hole is surroundings because we never update its position. In part 2, the system is the moon and ship since both move and interact with each other. The planet is surroundings because it's fixed at the origin of the whole thing. For part 1 initial conditions, the two things I had to set were the star's mass and the time interval. The lab tells us that the star's mass is about 2 times 10 to the 30th kilograms, and the time between data points is 1 Earth day, which is 24 times 60 seconds. And the velocity at each data point is calculated before the main loop by dividing the change in position by delta t, which gives us the average velocity between consecutive points. Inside the main loop, each iteration computes momentum at the start and end of each time step, takes the difference to get delta p, then divides by delta t to get F net. For the parallel component, we find the unit vector in the direction of motion, compute how fast the magnitude of momentum is changing, and multiply these together. The perpendicular component is just whatever is left after subtracting parallel from the total. Then to find the black hole mass, we rearrange F equals gmm over r squared to get m equals F times r squared over g times m star. The arrow scale is set proportionally to the star's distance divided by the force magnitude, so the arrows always appear a reasonable size relative to the orbit. For part 2, initial conditions, the moon's initial speed is calculated automatically using the circular orbit formula, square root over g times planet mass divided by radius, which gives us about 668 meters per second in the positive y direction. The ship starts 100 meters above the moon's surface on the side facing the planet, so it's initially very close to the moon. That's why I gave the ship a negative x velocity to immediately move it away from the moon before the moon's gravity could pull it and cause a crash. The total speed of about 680 meters per second keeps the ship gravitationally bound to the planet. For the iteration part, every 30 seconds of simulated time, the loop calculates 4 gravitational forces: the planet pulling the moon, the ship pulling the moon, the planet pulling the ship, and the moon pulling the ship. Each one uses the same formula, negative g times both masses divided by distance squared, times the unit vector pointing from source to object. Then Newton's second law updates velocity. V final equals V initial plus F net over mass times delta t, and position updates from the new velocity. This happens because both the moon and the ship this this happens for both the moon and the ship every single iteration. Comparing the two parts, the biggest conceptual difference is the direction we're working. Part 1 is an inverse problem. We have the trajectory and the work backward to find the force and then the mass. Part 2 is a forward problem, where we know all the forces and predict future motion. Part 1 also has only one moving body, while Part 2 has two moving bodies that interact with each other, making it a little more complex. What's the same in both is that the gravitational force is the only interaction, Newton's second law drives everything, and we're using finite time steps as numerical approximations of continuous physics. For sources of error, the biggest error is the large time step. 1 Earth day in part 1 means big gaps between data points, which is why the mass of the black hole varies. In part 2, I found the ship velocity by trial and error, so it's not perfectly optimized. Also, both parts treat the most massive object as completely fixed, when in reality it would move a little bit. And then finally, for the two discussion questions, for what does it mean? In part 1, F net equals dp over dt means the net force literally is the rate of change of momentum, not approximately, but exactly. So the parallel component tells you how fast the star is speeding up or slowing down, while the perpendicular component tells you how fast it's turning. In a perfectly circular orbit, F parallel would be 0 everywhere because the speed never changes, only the direction does. And then for the what if question, to model the entire system, including the black hole, star, planet, moon, and ship, you'd need to calculate all pairwise forces between every combination of objects. The black hole would dominate everything since its mass is about 10 billion times larger than all the other planets, and then all interactions would contribute, but they definitely wouldn't contribute as equally. And it's a clear hierarchy from the black hole gravity all the way down to like the ship's negligible gravitational effect on everything else.